Hi. Having looked at the way we use different instruments to record uh, earthquakes and the different types of earthquake waves, we now need to move on to consider what we actually do with that information. And to do this, we need to look at the scales that we measure earthquakes with. Now, we're going to be working in your themate booklets on pages 4 and 5 today. Let's start by looking at this. This is called the Mercalli scale. It's, it's named after Giuseppe Mercalli, an Italian geophysicist who came up with this way of measuring the effects of earthquakes. We describe this as an intensity scale. It's measured from 1 to 12. And you can see we use Roman numerals for this because it's a way of distinguishing it from the Richter scale that we're going to talk about a little bit later on in this lesson. If you look at the scale on this table, which is a copy of the one given in your booklet, you'll see that it's quite a descriptive scale. It goes from an intensity 1, which is really hardly felt at all, up through intensity 4, where it's actually felt indoors by a lot of people. Might feel like an accident with the building. By the time we get to intensity 6, everyone has felt that earthquake. It might make people run outdoors, might move furniture. By the time we get to an intensity 9, we see considerable building damage, maybe even moving off the foundations, noticeable cracks in the ground. By 12 then, it's total destruction. So you can see there are these descriptive points going up as we work our way through the scale. Now, this perhaps is less familiar to us than other methods of measuring earthquakes, because any one earthquake is going to have lots of these intensities, depending on exactly where people are. For example, the further away from an epicenter you are, the lower the intensity is likely to be. So there are some links there on the right hand side to the Richter scale, but that's not perhaps exactly as it works out. Okay, this is a good time to press pause and watch one of the associated videos that gives a simulation of different Mercalli intensities. Okay, welcome back. So we've looked at the Mercalli scale. Let's consider the Richter scale, perhaps better known than the Mercalli. The Richter scale, shown on this graph that you also have on page 4 of your booklet, shows some of the differences between the different earthquakes. Now the Richter magnitude is shown on the left hand side there, with 2 at the bottom, going up theoretically to 10 at the top. But to be honest, the way the Richter magnitude is measured, as we'll see, there's no actual maximum. In saying that, the biggest earthquakes we've ever recorded have been just over a 9. You can see from this graph that as we progress up the Richter scale, we get much fewer earthquakes happening every year. So down at a 2, for example, magnitude 2, we may have 1 million of those earthquakes a year. A 9, though, we will have perhaps one in every 10 years, or maybe even less often than that. I've given you some examples there of some of the different earthquakes from history. In particular, we're going to look a little later on at the Loma Prieta earthquake in 1989. On the right-hand side, you can see the equivalent energy release in terms of kilograms of explosives. We'll come back to that later when we're doing the calculations. For now, another time to press pause and watch the simulation of different Richter scale magnitudes in an earthquake. Okay, we're back. Let's look at how we actually can calculate this. Now, for this, we're working on question 2b on page 5 of our booklets. And for this, what you'll need to do is keep pausing as we work through each stage of the question. So the first thing I've asked you to do is to complete the column the amount of shaking on the left-hand side. With every step up the Richter scale, the amount of shaking increases by 10 times. I've put in a 1 there, so the one above that is going to be 10 times 1, which is 10. Press pause and fill in the rest of that column. Okay, if we complete that column, once we've got rid of Charles Richter there, we see these numbers appearing on the left-hand side there, going all the way up to 1 billion times where we started. Now, those numbers are a bit awkward, a bit clunky, so we can convert those into standard form. Press pause and do that now. Okay, if we look at these numbers in standard form, we can see that there's a nice pattern. And this perhaps shows us where we get our Richter magnitude from. Remember we said some of the biggest earthquakes are a 9. So the Richter magnitude is actually the power that we can see shown on that second column. So we can fill in the Richter magnitude like so. Okay, now we've got our Richter magnitudes, we can start thinking about the energy released. Go back to the graph on page 4. What's the relationship between each of those numbers in the equivalent of kilograms of explosives? What factor is it going up by each time? Once you've worked that out, we can then multiply that factor by the number we're starting with there, 1. Press pause now and fill in the rest of that energy released column. Okay, if we do the sums, we can see that each step up the Richter scale gives 10 times more shaking, but that requires 32 times more energy. So as you can see, by the time we get up to a magnitude 9, the amount of energy released is enormous. You'll notice that I've still got a row blank at the bottom here. Remember that every step up this scale is 10 times the one below. So it makes sense that every step down the scale is 1/10 of the one above. So we can even fill in a really very small earthquake. Of a -1 magnitude. Okay, we can then, just to deal with those numbers a little bit more easily, we've got standard form to show them. Okay. For those of you that had to go at digging deeper, or would like to have a go at digging deeper, this is how we actually calculate the Richter magnitude, looking at the distance away from the earthquake epicenter that an earthquake measuring station is, and linking that to the amplitude, the amount of shaking that there is. I've given you an example here of an earthquake measuring station that's 300 kilometers from its epicenter, And if we look at the shaking there on the seismograph at the top, we can see that the amplitude of shaking is just less than 100 millimeters. If we join those 2 points up, it crosses through our magnitude scale at a 6. So that would be an example of a magnitude 6 earthquake. Now I've given you some data there from the 2010 Haiti earthquake. Press pause now and see if you can work out the magnitude of that earthquake. Okay, if we look at this data, our first station, station A, and our second station, station B, if we draw our lines in, cross the magnitude scale at about a 7. So that particular earthquake, which was really quite devastating, there we are, had a magnitude of 7.0. Okay, we've now looked at the different scales and some of measuring earthquakes and the differences between those scales. We can see why that when we're looking at earthquakes as hazards, it's really only those above a magnitude 6 that really start to cause serious problems. Next time, we'll look at what some of those problems are.